Hello and welcome to our final plenary of the JpGU-AGU joint meeting. Myself, Satish, and Carol here. We are the co-chairs of the program committee this year. So it was an incredible week, and it continues to be. Wonderful talks, wonderful discussions. There is a special energy felt here. I can feel that. From the poster halls to oral presentations, to chance meetings and conversations besides a coffee. It's the energy and that is connecting with each other, learning from one another, and building foundations for trust, future collaborations. And whether you know it or not, in all those moments, big and small, all of you are living out our meeting theme, transformative science for Earth and life. Okay. The bonds you are establishing here are literally creating the transformative science, a science that is strong and vibrant and up to the task of taking on to our world's most pressing challenges. As we inspire the next generation of Earth and planetary scientists to pursue bold research directions and to confront problems of global significance, we are honored to welcome Jun Korenaga to deliver our Frontiers of Science lecture.
Serving as a professor of Earth and planetary sciences at Yale University, Korenaga's research explores the long-term evolution of Earth and terrestrial planets with a focus on understanding how Earth became a platform for the emergence and persistence of life. He places particular emphasis on mantle dynamics, viewing it as a central mediator linking planetary interiors, surfaces, and atmospheres over geologic time. Spanning a wide range of problems in geophysics and planetary science, often combining physics, chemistry, applied mathematics, and statistics to revisit long-standing questions from a fundamental perspective, Professor Korenaga's philosophy is intentionally broad and integrative, seeking to understand Earth as a coupled system rather than a collection of isolated components. A graduate of the University of Tokyo with bachelor's and master's degrees in geophysics and Earth and planetary physics, respectively, Professor Korenaga received his PhD in oceanography at the MIT Woods Hole Oceanographic Institute Joint Program. He was also a postdoctoral fellow in mantle dynamics at MIT and was the Miller Research Fellow in Theoretical Mineral Physics at the University of California in Berkeley. Please welcome to our JpGU-AGU joint meeting stage, Professor Jun Korenaga.
Thank you. Thank you very much. Thank you. Great. Okay, thank you very much for the kind introduction, and thank you all for being here, especially during the lunchtime. Today, I'd like to talk about a few different kinds of beginnings. I've been working on the early Earth for the last 10 years or so because I've been fascinated by its connection to the origin of life. This explains the first two elements in the subtitle, but the subtitle also has one more element, and this is because I was asked by the organizers to include some messages for young scientists, and I hope you see some connections among those three elements by the end of this talk. Okay, let me start with something very basic. Earth's history spans about 4.5 billion years, and we divide it into 4 eons: Hadean, Archean, Proterozoic, and Phanerozoic. These terms all have Greek origins: Phanerozoic for visible life, Proterozoic for earlier life, Archean for ancient, Hadean for hair-like. You probably know this already, but the way Earth's history is divided like this has a good reason, and it's important to understand it. If you look at the so-called geologic timescale, like the chart shown here, you notice a striking imbalance. The Phanerozoic eon the last 540 million years is incredibly detailed. It's divided into 3 eras, Cenozoic, Mesozoic, and Paleozoic, and each era is further divided into periods, epochs, and then ages. This is largely due to the Cambrian explosion at the beginning of the Phanerozoic, which resulted in the rich fossil record that follows. In contrast, everything before that, including the Proterozoic, the Archean, and the Hadean, they're often lumped as the Precambrian, and it's treated much more costly. So already, our understanding of Earth's history is highly uneven. The recent past is well resolved. The deeper past become progressively blurred. So Phanerozoic has lots of fossil record, which allows us to build very detailed stratigraphy across the continents. And we have even direct record of seafloor spreading for the last 180 million years. So it's possible to reconstruct Earth's surface in considerable detail for the Phanerozoic eon. For example, here you see paleogeographic reconstruction from the present day back to 600 million years ago. We can track the breakup and assembly of supercontinents like Pangaea. We can study continental flattening due to sea level change, paleoclimate, and large-scale tectonic evolution. So that's the Phanerozoic. An important point here is that the boundaries between these geologic eons are all related to the abundance or paucity of data. There are still lots of rocks with Proterozoic ages, but it's harder to find rocks with Archean ages, especially early Archean ages. And there's no rock with Hadean ages. We only have zircons with Hadean ages. And this is largely because Earth has plate tectonics, which keeps recycling the surface by subduction. As you can see in this map of crustal age, the ocean floor is not older than 200 million years old. It's all blue. And the continental crust, partly because of its buoyancy, tends to stay longer on surface, and its mean age is about 2 billion years old. But you can also see that older continent is more rare. If we limit ourselves to, say, the last 3 billion years, that is only back to the mid-Archean, we still have enough data to constrain reasonably reliable estimates on what was going on there. I started to work at Yale in 2003, and for the first 10 years, I focused on this part of Earth's history. Even though the record is incomplete, it is still rich enough to support quantitative analysis. For example, as shown here, we can estimate the thermal history of the mantle using petrological data. The x-axis is age, and y-axis is mantle temperature. And these black dots are petrological estimates. And you can test different kinds of, different theories of mantle convection against these data to see which one makes most sense. But when we go further back to the early Archean and Hadean, the situation changes dramatically. We just don't have many rocks from the early Archean. And for the Hadean, as I mentioned earlier, we only have zircon grains. And yet, this is arguably the most fascinating period in Earth's history. This is when the moon-forming giant impact occurred, when the Earth likely had a deep magma ocean as a result, when the first oceans formed, when the plate tectonics may have begun. And most importantly, when life emerged. And this is why I started to think about how we can better understand the early Earth, because if you come to think about it, the emergence of life on the early Earth is such a miraculous event. To appreciate this point, we may want to step back a little and think about the origin of life in the universe. What's shown on the left is the history of the universe, and it's simply amazing that we now know this much detail. Of course, we still have some ambiguities in the earliest possible fraction of the history, but after that, our understanding is fairly solid. Things proceed in the order of electron-weak transition, quark-hadron transition, nuclear synthesis, matter domination, recombination, galaxy, stars, and solar system formation. And what's shown on the right is Darwinian evolution of life, which is equally fascinating, and we know it in great detail. But if you look at these two side by side, there's a huge gap in between. We understand how the universe evolved physically, and we understand how life evolves once it exists. But how to go from this physical evolution to biological evolution is still a total mystery. As you probably know, many people try to address the origin of life in the universe, but we are still very far from answering this question. There are a few reasons for why origin of life is such a difficult question. First, there is no direct data, so everything has to be theoretical in nature. Second, organic chemistry provides almost infinite possibilities. There are just too many reaction pathways one could imagine. And third, early Earth was likely very different from the present Earth. This last point is as important as the first two, but it's not always fully appreciated. For example, there is a famous book by Freeman Dyson called The Origin of Life. Its second edition was published in 1999. This is very well written, and is highly recommended if you're interested in this sort of thing. But here's an excerpt from this book. Generally speaking, it can be said that the geophysical and chemical stages of prebiotic evolution are reasonably well understood. Theories of geophysical stage can be checked by abundant observations in the field of geology. Many details remain to be elucidated, but the geophysical and chemical stages are no longer shrouded in mystery. When I first read this more than 10 years ago, I was like, what? Seriously? I think I know Earth's history reasonably well, but this is simply not true, even today. In his defense, this book is about the main point of this book is about the biological stage of prebiotic evolution. So I do understand he wanted to be done with this geophysical stuff so he could move on, but this statement is simply not true. So let me come back to this list again. The lack of data is unavoidable. The complexity of organic chemistry is also unavoidable. But the third point, and the third point is also a real difficulty, but the nature of the early Earth is something we can work on as Earth scientists, and this is a great opportunity for Earth science to make meaningful contributions to the debates on the origin of life. So when it comes to the early Earth, we have quite a few very basic questions, such as, did we have pre-tectonics back then? And we like to know what kind of atmosphere and ocean we had. And did continents already exist in the Hadean? If so, how much? And how much of continents were above sea level? Even if we had lots of continents, it doesn't mean we have lots of dry land, but without knowing the extent of exposed landmass, it's difficult to talk about early Earth environments. Now, being able to address these simple questions is another reason I'm attracted to the early Earth. We may think that we already know a lot about how Earth works, at least to first order. But in many cases, our understanding is largely empirical. For example, we still cannot explain why we have plate tectonics on Earth. We know we have plate tectonics going, but it's really difficult to explain why we have plate tectonics. And when we discuss the early Earth, we need to go beyond this usual empirical understanding and ask ourselves how well we understand a given process or phenomenon. To make my point a bit more concrete, I like to focus on this last question, how much dry land there was. Because the dry land question is particularly important for the origin of life. As you may know, there are two major opposing camps about how life originated on Earth. One is a variant of Darwin's warm little pond speculation, which requires exposed landmass on which the so-called wet-dry cycle can polymerize organic molecules like amino acids into proteins. The other camp relies on certain chemical reactions we can expect at submarine hydrothermal fields. It's really difficult to tell which is more promising because abiotic synthesis of biomolecules is simply just so hard. But if there was no dry land on the early Earth, then it would categorically reject this warm little pond hypothesis. So if you want to pursue this wet-dry cycle idea, you probably want to make sure at least you did have a piece of dry land on the early Earth. But this dry land question is actually very difficult to answer. To see that, we can start with this textbook question about isostasy. If you have taken an introductory course on geology or geophysics, you may have seen something like this before. This is about the present-day situation, present-day average structure of the continental and oceanic domains. And we have the continental crust, about 35 kilometers thick with density of 2,500 kilograms per cubic meter. And we also have oceanic crust. It's 6 kilometers thick. It's a little denser than continental crust. And below it, we have mantle, which is much denser. Using isostasy, we can figure out the depth of the ocean. And if you do the math right, you get 6.6 kilometers. So this is easy. This is almost a high school level question. Using the same figure, we can also ask more fundamental questions, like why the continental crust is 35 kilometers thick today on average. And it's very difficult to answer this question. By contrast, it's easy to answer why oceanic crust is 6 kilometers thick, because we have a theory for the genesis of oceanic crust. Oceanic crust is a product of mantle melting beneath mid-ocean ridges. And if the mantle was hotter, it would melt more and give you thicker oceanic crust. So the thickness of oceanic crust is a function of mantle temperature. But we don't have an equivalent theory for the genesis of continental crust. Of course, we have some ideas for how to create continental crust, but our understanding is not as quantitative as that for the oceanic crust. And this lack of a quantitative understanding is a bit problematic when it comes to early Earth problems. Suppose we have to speculate on the spatial extent of dry land, and let's assume, for the sake of simplicity, we have the same masses of ocean and continental crust as the present day, and the mantle has the same temperature, so oceanic crust is 6 kilometers thick. If the continental crust is 20 kilometers thick instead of 35 kilometers thick, it has to cover the 70% of surface area to conserve mass. And if you apply isostasy, the entire continental crust will be covered by oceans. So there will be no exposed landmass. And the situation is much worse for the actual early Earth problem. One thing we are sure is that the mantle was hotter by 200 to 300 kelvins. So we had a much thicker oceanic crust, probably like 20 kilometers. But this is the only thing we are confident about. We are still debating how much of continental crust we had, and that's about the mass. And to convert it to volume, we need to know the density, which depends on the composition, which is also controversial. And for the oceanic side, the ocean volume can be different in the past, because ocean volume is not a static constant. It's controlled by the dynamic balance between water degassing from the mantle and water regassing into the mantle, which is called the deep water cycle. So to answer this dry land question for the early Earth, we have to combine practically everything we know about how Earth works in the past and also in the present. And if we understand them better, we can answer this early Earth question with more confidence. And this is my current best guess about this issue by combining what I know about those things in a self-consistent manner. In the early Earth, we had a shallow ocean and not much of continental crust, but the ocean volume kept growing. And at the same time, content started to grow. If continental growth was fast enough, we could have a large amount of exposed landmass in the mid-Archean. But by the late Hadean to the early Archean, the ocean probably became deep enough to inundate most of the continents. So the first 1 billion years of Earth's history probably witnessed a dramatic change in the ocean continent configuration. And this is just a guess to be revised in the future, but this kind of detail of early landscape evolution matters a lot for the origin of life problem. Okay, let's change gears a bit and take another example, this time from geochemistry. This is again how a seemingly simple question can turn into very complex problems. This is a cartoon visualizing the amount of precious metals so far mined on Earth to explain why we have to pay a bunch of money to get things like gold and platinum. But the fact that these metals exist on Earth's surface at the level we can mine is actually quite amazing. This is because gold and platinum are both so-called highly siderophile elements. This is a periodic table with a cosmochemical flavor, and the elements with blue backgrounds are siderophile elements, meaning they love iron. So when the building blocks of Earth melt and separate into the rocky part, which becomes the mantle and the crust, and the metallic part, which becomes the core, these siderophile elements, blue stuff, like to be in the metallic part. Now, among these siderophile elements, those 8 elements bounded by red lines, including platinum and gold, are highly siderophile elements, so they really like to be in the core. But surprisingly, the Earth's mantle has a non-trivial amount of highly siderophile elements as shown here. The vertical axis is the abundance normalized by the chondritic abundance. And the abundance of Earth's mantle is shown by this red line at the level of 1%. And this is about 3 orders of magnitude greater than the level expected for highly siderophile elements, which is indicated by this blue curve. Equally importantly, this mantle abundance is in the chondritic proportions, as you can see from its flatness of this curve. This has commonly been interpreted to mean that these elements did not experience the metal silicate equilibrium, because if they did, the abundance should deviate from the chondritic proportions, just like this curve expected for the predicted concentration. So to explain this high abundance of highly stereophile elements in the chondritic proportions, people propose the so-called late Venier hypothesis, which goes like this. Earth's formation was pretty much completed by the moon forming giant impact, and most of the mantle was molten by this impact, which helped finalize the formation of the core. And because molten silicate and liquid metal can chemically equilibrate very efficiently, almost all of these highly stereophile elements must have been sequestered into the core by this time. But even after the moon-forming giant impact, there were still lots of leftover planetesimals hanging around, and they continued to fall onto the Earth. And they are called the late Venier or late accretion. And if the amount of late accretion is about 0.5 to 1% Earth mass, it's sufficient to explain the observed mantle abundance of highly stereophile elements and their chondritic proportions, because this addition just affects the mantle. Okay? This idea was originally proposed in the late 1960s, and it's now part of the standard planetary formation theory, as you can see here. The x-axis is time in the log scale, and y-axis is planet size in the pseudo log scale. This red line shows how Earth grows by a series of different accretionary processes, and the last stage is late Venier or late accretion. The late accretion is not just a convenient explanation for mantle chemistry, because the moon preserves a clear record of continued bombardment of leftover planetesimals after its formation. But here's a problem. Both the lunar crater record and asteroids indicate that the size-frequency relation of those planetesimals follows the power law, like this, as shown to the left. Shown to the right is a famous Gutenberg-Richter law for the size-frequency relation of earthquakes. And as you know, we have lots of small earthquakes and a very small number of very large earthquakes. But the total energy released by all of those earthquakes is occupied by this very small number of very large earthquakes. Just like that, the total mass of late accretion is dominated by these very rare, very large late accretion impactors. So just to remind you, the mass of the moon is about 1% Earth mass. So large late accretion impactors can be as large as the moon. This movie shows an impact simulation with a lunar size impactor. Both the target and impactor are chemically differentiated, as you can see on the left panel, and the right panel shows the temperature. Late accretion impacts can be highly energetic, as you can see. It can create local magma motion, and the core is heated up quite substantially. By the way, I should note that this particular movie about the late accretion onto Venus, which is a bit more energetic than those onto the Earth, but the overall characteristics is basically the same in this context. Okay. I ran this movie again, and this time, please pay attention to this impactor's core, this white stuff, and where they end up. Some fraction of the impactor's core goes directly to the target core, and this impact simulation runs about 11 hours because it's very computationally expensive calculation. So we cannot do more than that. But using fluid mechanics, we can estimate how those white stuff in the mantle move afterwards. And it turns out they all eventually sinks down to the core over the time scale of a few million years. So if you take this simulation at face value, later accretion, which is proposed to explain mantle geochemistry, doesn't seem to do its job because this white stuff, which is supposed to contain highly sulfide elements, they all sink to the core. But if you look more closely at what could possibly happen during late accretion impacts, it is possible to keep the impactors metallic components and mix them into Earth's mantle. This is because when a shallow magma ocean is created by a large impact, you almost always have a thick, partially molten mantle beneath it, into which the metallic components can infiltrate. This infiltration can happen very quickly, like a day or two. And this densified partially molten zone suffers from gravitational instability and sinks to the core mantle boundary region in the next about 10,000 years, during which it solidifies by adiabatic compression. And then this metal impregnated mantle is gradually entrained by mantle convection, and highly sulfide elements are distributed within the convecting mantle. This possibility is interesting because it can naturally explain the mysterious future of the present-day Earth mantle. From seismology, we know that the lowermost mantle has two large domains of low shear velocities, these red regions here, one beneath Pacific and one beneath Africa. And they are called the large low shear velocity provinces, and they seem to be the source region for most of hotspot magmatism. The origins of this anomalous seismic velocity structure has been debated for the last few decades, so we have many ideas. But this late accretion impact explanation is promising because it can connect a few disparate aspects of mantle geochemistry and mantle geophysics in a unifying fashion. Simone Maki and I wrote a review paper on late accretion impacts last year because there are just so many interesting processes that can be initiated by late accretion impacts, large and small. And as you can see here, they span a vast range of timescales from days to billions of years, so over 12 orders of magnitude. For mantle geochemistry, I talk about the three-phase mixing, Rayleigh-Taylor instability, and convective mixing, but there are other processes that are important for the atmospheric and ocean evolution, crust evolution, and also core-mantle interaction. In particular, moderate-sized late accretion impacts can potentially produce a reducing atmosphere over the time scale of millions of years. And the creation of such a reducing atmosphere is generally considered to be important for the origin of life. So I talk about just two examples, but I hope that you saw the same pattern here. Dry land question and the late accretion problem, for both of them, we are simply asking, what did the early Earth look like? And trying to answer this question naturally leads to a plethora of fundamental inquiries on how Earth works, to the extent that we have to ponder how well we understand even the present-day Earth. Okay, as I mentioned at the beginning, I was asked to have some messages for young scientists in my talk. So I was thinking for a while what I should say in this occasion. And I thought maybe I can share what I read when I was young, because for some reason, this has stayed with me for all those years, and I'd like to explain why this particular phrase left such a big impression on me. When I was an undergrad in Tokyo, I had lots of time to read books, and one day I came across this aphorism by Paul Valery. The original French text is shown at top, followed by English translation, followed by the Japanese translation, which I read back then. Most people stop at the first stages of their trains of thought, with the result that in the end, their whole mental life is found to have consisted of beginnings. Valéry was a French poet and critic who was very active around the turn of 20th century. And this aphorism was a satire on the trend he observed in France at the time. With the rise of mass media like newspapers and tabloids, people became increasingly drawn to flashy, newsworthy ideas, and most people didn't take the time to think things through. Interestingly, he could have said the same thing to us surrounded by social media, but when I first read this, I took it in a different way. Being naturally positive, my own interpretation is this. Everyone can have the beginning of a great idea. The difference is whether you keep going. This probably qualifies as a sheer misinterpretation of Valéry's original text, but this is how I remember that phrase, and after doing research for more than 3 decades myself, I think there is some truth to it. I do think everyone can have the beginning of a great idea. Just in case you're wondering how to get the beginning, here's one suggestion. You can ask yourself whether you can explain certain conventional wisdom in your field from first principles. You may be able to discover something no one has ever thought of, or at the very least, you can solidify your understanding of the basics in your field so you don't lose anything by doing it. And chances of finding something interesting are actually quite high in earth and planetary sciences. In some fields, like cosmology or high-energy particle physics, large-scale collaborations naturally concentrate attention on a small number of major questions. But in our field, there are just so many fascinating problems that almost everyone ends up pursuing their own agenda. And that means there are still many stones left unturned. And in exploring nature, there's perhaps no field more compelling than earth science. By considering the evolution of Earth as part of the solar system, we are led to reflect on both the vastness of the universe and the remarkable diversity of the biosphere. And with that, I'd like to conclude my talk. Thank you for your attention.
Yeah, wonderful talk. Thank you. Yeah, it was great. So your talk ended with the idea that everyone can have the beginning of a great idea. Yeah, that enthuses a lot of youngsters here, I'm sure. So how can you identify a good beginning or problem worth pursuing?
Okay, there's one thing I always tell my students, so what to work on, and I always tell my students to ask 2 questions by themselves. One is, who cares? And the other is, so what? And this means that, so I think, you don't have to exactly follow this, but usually if your research can reach to more, greater number of people, it has potential to be appreciated by many people. So so you need to keep asking the potential importance of your problem at the beginning. So the thing is, okay, there's other thing I also tell my students, because it takes time to do one project, even if it's trivial, because you have to work on it and make figures and write papers and submit and then review, and you have to revise. So So everything takes time. So if you have to work on it and write a paper and publish it, I think it's worth more if you work on a more important problem. So the how to set up a problem at the beginning is probably important.
Excellent. Yeah. Great.
So you mentioned that the early Earth is data poor but conceptually rich. So how do you think you can do rigorous science in such a regime? And my own question is the conceptually rich part, especially given the book that you quoted in the beginning, has some concepts that are
yeah. I think so. So the kind of question I tend to get asked is that how do you test your theory? Because it's difficult because there are many data. But my take is that those data, for example, geocongruent, geochemistry geocongruence, they reflect like a real Earth processes, so it can be very complex. So your theoretical model has to have sufficient realism to it, so you can compare your model prediction to the actual data. Because even if let's say if your model is simple, but that doesn't mean your data is also simple. Data is usually very complex. So it's really important to have a good balance between the kind of data you want to interpret and the kind of model you want to develop. Because if they're unbalanced, then you could misinterpret what this precious data could mean. And because we are kind of in people working on the theoretical side, so there are a lot of work needs to be done. So but we have to be patient so that we have realistic, reasonably. It doesn't have to be super complicated because then it may go nowhere. But your model has to be reasonably realistic so that you are confident in comparing your model prediction with actual data, and this takes time.
So I'm going to ask a follow-up question that's not on our list. So what about analogs? Like if one of the preconceived ideas is that plate tectonics was operating or not operating in the Archean, for the model concept, can you take observations, geophysics, geochemistry, et cetera, from times when we know for sure that there's plate tectonics, and how do you then match it to some place that just that has like very little data? Do you take these sort of concepts from the present and see how they apply?
Oh, so we for the onset of plate tectonics and sort of that kind of question, we need to, because from Hadean time, we just don't have much data because we have geocongruence, but they are coming from highly localized areas. Most of it comes from Jack Hills in Australia, which is a very small area. We are getting more data from South Africa, but still, but the volume of data is still very small. For the Hadean plate tectonics possibility, the one line of logic I usually bring up is you need to explain the atmospheric evolution. So if you're just looking at what rocks do, you may not be able to tell when we have plate tectonics in the Hadean or not. But because we have the moon, we are pretty sure we have some kind of giant impact. And because giant impact, which of course, I just showed the impact simulation for late accretion impact, which is much, much smaller. But giant impact is it's huge, so most of the mantle must have been molten. And then if you use our understanding of how much of carbon we have in the mantle, then carbon dioxide is not very soluble to the mantle. So if you create magma ocean, then most of the carbon in the mantle should be in the atmosphere. And when magma ocean solidifies, then those atmospheric carbon should be left in the atmosphere. So right after magma ocean solidification, the early Earth must have looked like present-day Venus, so a very dense carbon dioxide-rich atmosphere. But from geological record, we know atmospheric carbon dioxide should be less than 1 bar by the beginning of the Aki. And so you need to go from like a Venus-like 100 bars of carbon dioxide to less than 1 bar, like by the 2.8 GA. And the only mechanism to make it happen is by plate tectonics. So plate tectonics is a very efficient the way to sequester carbon from the atmosphere to deep mantle. So this is the one thing I always tell to the people who like to have non-plate tectonic regime for early Earth, like a stagnant heat convection. It's okay for you to believe in stagnant heat convection because, of course, there's no evidence for plate tectonics because we don't have rock. But if you do so, you also have to explain how you go from this Venus-like atmosphere to more moderate atmosphere during Haitian time.
So I just want to comment that that's such a great example of how broad your research is. I'm an earth scientist. I would never have thought about looking at the atmosphere. So that's a very nice example.
Wonderful.
Thank you.
Wonderful. So you were talking about lot about origin of life. So if you could answer just one question about early Earth, which would most advance our understanding about origin of life?
Yeah, that's related to what I have just said. So, if we had a plate tectonics, in the Haitian or area, again, because present day Earth is basically every aspect of Earth's processes is affected by plate tectonics. So if you don't have it, if you don't have plate tectonics, we probably have very different situation, and it's really, our understanding of it is very limited. But so having plate tectonics is fundamental kind of, the problem. If you don't answer this question, then it's really difficult to do other things. So you have to settle this question so that we can think about more details.
Just to follow up that point, in one of your slides, you have marked that it's a reducing condition in the atmosphere. So
what condition?
Reductive.
Oh, yeah, reducing. Yes,
yeah.
Right.
So how do you think? Why did you reach that point?
Oh, okay, because biomolecules are all reduced. You have a hydrogen in it, so to create things like amino acids or like nucleotides, you have to be in the reducing environment. So right now we are highly oxidized atmosphere, so we may think we need oxygen, but if you have this kind of atmosphere in the early Earth, then you never get to create biomolecules abiotically. Okay, we can create those molecules now because we have biology already. But if you don't have biology, you need to create in some way like reducing conditions so that you can synthesize biomolecules without using biology. Yeah.
Wonderful.
So I was interested in your whole discussion about the importance of dry land. So do you think this question has been relatively underappreciated? Do many people talk about it?
I think the situation, so I started to work on this kind of issue more than 10 years ago, but during the last 10 years, the community feelings has gradually changed. So more and more people in the origin of life community start to appreciate the importance of understanding early Earth environments. But traditionally, people working on the prebiotic chemistry is that if they find some interesting prebiotic processes, and if they for that processes you need this kind of temperature, this kind of the chemical condition and so on, they cook up. They assume early Earth must have been like this to make it happen, but that's the other way. That should be the other way around.
So, how has recent work on late accretion changed your view as a total on the Earth environment?
Okay, because before I met Simone Maki, because I'm like a traditional mantle geodynamicist, so we are not used to think about this external energy input. So I tend to think it kind of nuisance. If we can ignore, it's better. It's because it's simple. But Simone showed me that kind of impact simulation. So it's so energetic, and you can just change the total energy like a level just by one large impactor. And like even if you have a smaller impactor, you have substantial influence on how mantle dynamics should operate. So but the data acquisition impacts are most important for the first few 100 million years. So just the Hadean processes, but these Hadean processes, this Hadean time is very important for this original life equation problem. So I now think it's very important to study more what could possibly happen with data acquisition impacts, so we can discuss those things with more confidence.
Great.
So your talk spans many fields, right? Geodynamics, geochemistry, planetary science. So the question here is, what are the biggest barriers to truly integrating these fields? But I'm curious about how you decided, like the answer to your plate tectonics question. How did you decide, I'm going to look at the atmosphere, I'm going to look at Venus? How do you make those decisions, and why don't other people do that?
It's hard to say why other people don't do it, but I feel like I'm always a student. I entered the college at the age of 18 and just stay in the college. And I keep studying, and so I enjoy learning new things. So, as a result, I end up doing those more, end up working on those different disciplines. But it's just a result of keep learning what I find interesting.
So, but in terms of barriers, which is a little bit to my question, what happens when you do that? Like, you're not officially a planetary scientist, right? I mean, do you have credibility issues? Or what kind of barriers do you see for other people to be able to do these kind of linkages?
Okay, so so at the beginning, it's hard to read papers in other fields, like lots of jargons, and familiar with the logic. But my experience is that if you keep reading, and I think if you read more than 100 papers, then you get comfortable with what's going on. So I think you just keep reading is a key.
Well, what about, with AI? Now that you can load up a bunch of papers into, Notebook LM that can summarize it, and you can then start asking questions to jump over these kind of barriers.
Yeah, I see. Yeah, if you have good fundamentals, and you can, because they hallucinate so often, so you really have to make sure the answer, their answers make sense. So you have to be able to tell if they are, doing the job or not. So after you bring yourself up to the point, then AI will be useful. But if you are not ready, then you may not benefit from using AI. So I think I think it's a good question, because we are in a very tricky times to how to make better use of AI. But AI can be very useful. You can quickly not ChatGPT, but there's other AI that totally that purely based on the existing publications. They don't give you fake DOI kind of stuff. So, but you have to be able to make good use of them, and so there is no shortcut to that process.
I guess you still have to. In the example I gave, you still have to upload the publications that are behind the paywalls that you think are important. So there's a selection process there, as opposed to just using ChatGPT or Claude. Can maybe help with sort of focusing the questions.
Right. So if you can't ask good questions to generative AI, then you will benefit from it. Yes.
Okay, so it's almost getting time. So once again, I would like to thank you for your great talk, and thank you so much.
Thank you.
Thank you.
Yeah, thank you. Thank you. Thank you.
Congratulations.
Thank you. Yeah.